All right, welcome to this overview video for Lab 2. All right, so in the lab, we're working on several things. Last time we looked at the workflow, where we started by taking an assignment that you accepted, which put a repo into GitHub, and then you were able to clone that repo using VS Code to Box so that you could load everything up into Vivado. There's a lot. So we're going to go through this some more, but this time we're going to start to focus on the actual Verilog. All right, so we've talked a little bit about this in class. I've introduced to you how to define a module, but we're going to keep working on that. So the first thing I want you to remember is Verilog describes circuits. It's not the same as programming. All right, so what I wanted to do is to illustrate this process with a very, very simple lab. What we're going to do is we're going to implement some logic functions. We're going to do 4 logic functions. In real life, you wouldn't do this because it's too simple of a project. And we're going to separate each of these logic functions into modules. They're so simple that normally you wouldn't separate this kind of thing into separate modules. But the point is to look at the workflow and how you put things together and to start to think in hardware. So we're going to write some simple modules. You're going to get some practice at doing that. After that, you need to learn how to interface modules together. So we're going to look at connecting modules. We're going to talk about that a little bit in this video. You're going to build a top design that puts together smaller pieces. From there, we're going to jump into a different video where we're going to look at how would you actually put code into VS Code or Vivado and run some simulations. We're going to do that. And then we're going to work through testing your code. You can either do that in VS Code or you could do that in Vivado. I want you to be able to use VS Code though for real simple things so that you can work outside of the lab environment, and because VS Code is a development environment that I hope you become familiar with. All right, so those are the learning goals. Let's jump in. All right, so what I have here is the results that we're going to end up with. I want you to know, a lot of times we would call this the ERT. ERT would be the expected results table. All right, so at first I was going to have you calculate that, but there's already a lot going on. This is pretty simple. What I've got here is 4 logic functions. Here's F0. You can see the logic. It's A ended with B. This is the OR symbol in Verilog, and is ampersand. So here's a simple logic function for F0. For F1, we use this symbol. Okay, that symbol is exclusive OR in Verilog. So we're going to exclusive OR all the bits together. Then there's another function, majority function. It outputs a 1 when more than 2 outputs are a 1. You can see why it would be called a majority function. And then the last one is just this logic function that uses the tilde is a complement in Verilog. Okay, so the point is not which logic functions. This is just to illustrate something that we can put together. All right, and so we want to know if we're putting it together, if we're putting it together right. Okay, so what we're going to do is we're going to look at test benches that test all the modules along the way. So you're going to need to go to this results table. If, for example, I'm running the test bench on logic function 0, you would need to look at this column here to figure out, oh, are my answers right? Okay. And then later on, what we're going to do is we're going to put everything together in hardware and send the answers to the 7-segment displays that we used last time. So you would also need to keep track of, here's the expected results for the hex output for the different test vectors that we're putting in as the inputs. All right, so that's where we're heading. We're putting together 4 functions. We're going to piece this together. You'll see as we go. Okay, so the next thing that I want to talk about is this idea that we are talking about modules, all right? And so modules are a way of describing circuits. I think of a module as a building block, okay? So one thing you can do is you can make schematics that show how modules connect together. All right, so I think the idea of thinking in schematics is important because we're describing hardware, and hardware is circuits, and the way we describe circuits are schematics, okay? So rather than showing the logic functions within each of the 4 logic functions that I'm implementing as modules, I'm going to show the modules as blocks, okay? So this is important because this is an RTL diagram. You're going to hear me talk about that a lot. This RTL diagram is the schematic. I can zoom in. Remember in the lab last time we showed the schematic from RTL and Vivado, and we could zoom in and actually see the circuit. But a lot of times we want to work more at the functional level. So I have these 4 functions. Each one of them has a box. Each one of them has inputs, and each one of them has outputs, all right? So in this toy example, I didn't want to use the same input labels for all 4 functions. So you see here in function 3, okay, in function 3 I have inputs in underscore A, in underscore B, in underscore C, and in underscore D. Those are the names, okay? For logic function 2, I took a different approach because I want you to be able to handle different approaches. I did a vectorized input. So we have inputs here as the input to function 2, and it's a vector. So notice in this diagram, I'm showing a vector. That means this is actually a wire with 4 wires, and invec is also going to be a vector. We'll talk about that when we get to some of the implementation videos. All right, so the point is I'm using different inputs, and each one of these has a different output name. All right, but I wanted to put this together into a top function. Okay, so I want to test them all together, and so what I can do here is have inputs and outputs in a top function. All right, so in general for this class, I'm going to have, let me change this so I can highlight it. Inputs, we're going to look at outputs, and we're going to look at wires. Okay, so in general, what I will do is I will highlight outputs to be blue, inputs to be red, and wires to be yellow or gold. Okay, so in this case, we don't have any wires, but you can see, oh, it's the wrong shade of blue. Let me change that. Okay, so this shade of blue is the outputs. All right, so I can see here that I have an input vector. All right, we're going to talk about how to do that in another video, but I have one input vector that runs all the inputs, even though the inputs have different names within the modules. I'm going to run all of those with the same input vector. All right, so you see I have that defined in my schematic. All right, so the nice thing about a diagram like this is that when it comes time to write code, you can look at the diagram and you know how things are connected together. So we're going to find that there's a pattern for instantiating different modules within Verilog. And if you look at the diagram, the RTL diagram, it tells you how to make the connections. So these are going to be important. All right. So let's focus on those. All right. The next thing I want to do is show you there's a wrapper. Okay. So we talked a little bit about this last time. Typically with a design, there's a function that you're trying to implement. Okay, maybe it's an adder, all right? And then once you implement that function, you might want to use it on different hardware targets. Okay, so in this particular case, we're using the Basis 3 boards as hardware targets. And so typically we try to separate the functions from the actual hardware target so that if I wanted to change the hardware target, I could do that. So we do that with the tool of using a wrapper. Okay, so notice that I have a new block here in this diagram, okay? And this new block, I'll point to it in a different color. This new block is the same module name as the block I just did, okay? So I'm zooming in and I'm gonna put this top module into a wrapper. All right, so the wrapper is hardware dependent, and what I wanted to do is take the output of the 4 logic functions, logic out right here, and decode that into one of 16 digits. All right, so for example, what this does is if you get all zeros here, then decoded 0 shows up as, decoded as a vector. So if I have all zeros, decoded 0 would be a 1. Everything else would be a 0. Okay, so if let me do another example. If I put in, for example, this is binary 2. Okay, so 2 would be a 1, and all the rest would be zeros. Okay, so what that does is it tells me which digit I want to turn on the 7-segment display. All right, and so there's logic here that decodes, if this is a 2, it turns on all the segments to light up a 2. All right, so you don't need to know exactly the details, but the point is, I took this top logic function, okay, I connected it to something that would let me show things on the display. That shows up in the wrapper because the 7-segment thing is hardware related, and I chose to put that in the wrapper this time. Okay, so the nice thing about this is it shows you inputs and outputs for each of the modules. Here's an input, here's an output, here's the input, here's the output, and from that, you can use that to instantiate your designs. Okay, so this is the basics ideas. We're going to go through here. We're going to take these RTL diagrams and we're going to turn this into code for this lab.